Okay, so I think you have a homework assignment due tonight, right?
Yes.
So are there any questions?
Yes.
All right, fire away.
On
The recurrence. Yeah, you write the recurrence from the code.
Yes. Is
Okay.
the recurrence the Tn?
Oh, yes. Okay, so the question is, what exactly is the recurrence? The recurrence is T of n equals brace, and then you have one case for if n is something, and then you have another case if n is greater than that.
Okay.
This is the recurrence.
Okay, and then if there are 3 cases, then we'd have 3 lines?
Well, no, because the 3 cases, 2 of them are not recursive.
2 of them are just base cases?
So, yeah,
Okay.
yeah. Oh, right, there was a Fibonacci one, right.
Yeah.
Yeah. But see, I mean, those are the, see, in the recurrence, those execute, they're not recursive calls. So both of those are base cases. So we combine them into just this one. Now see, look, here's the thing, you guys. This was at the end of class last time. Remember what we wound up doing is we had numbers, like we said, in this example of the factorial, we said T of n is 2 if n is less than or equal to 0, and then we said T of n minus 1 is T of n minus 1 plus 3 if n is greater than 0. And the way we got that 3 is we said, well, the if statement is one execution, and the multiply is another execution, and the return is another execution. And so we had these constants here, right? So when you do your homework, it's okay to do it not in this form where you have these specific numbers, because after all the numbers will be different in your first base case and then different in the second base case. But what we're saying then is that any constant, like 5 is big theta of 1. Also 6 is big theta of 1. See, these are easy to prove. It's just a constant. I mean, you can find a constant such that 6 is always bounded below by 1, and you can find another constant such that 6 is bounded above by 1. Right? So you can combine those, and because they're just constants anyway, so just combine those into the one base case and make it big theta of 1. Yeah. So okay, look, big theta of 1 does not equal big theta of n. All right. In fact, one of these is the big O of 1, and the other one is the big omega of 1. Big theta of 1 is bounded. What is big theta of 1 worse or better than big theta of n? It's better. 1 is bounded above by n. You see what we're saying? And furthermore, n is bounded below by 1.
So they should
So this is,
the same
but they're not. See, if you have an algorithm that is big theta of 1, then it doesn't matter how many data points, how much data there is, it will run the same amount. If you double the number of data, it will change.
Okay.
For example, if your algorithm is simply finding the nth element of an array, and you do like it doesn't make any difference if you do, like x gets array sub 1,000 or x gets array sub 5,000. Okay. It just takes one, because it goes directly to it. So that's an example of, of an algorithm that is big theta of 1.
Got it. Okay. Yeah, I think that's what I was.
But this n is this is linear.
Got it. Okay.
All right. So if you double it, yeah. Okay. Good. So these are all good questions.
Thank you.
Yeah, and this is a way of thinking, you guys. All this asymptotic way of these tools that this is all very basic. This is just, it's elementary. It's basic tools for analysis of algorithms, and we need to start thinking this way. Our job here is to get some intuition, or to get some the skill of being able to see the code and be able to determine just at a glance what the big theta is. Do you see what I mean? So what we're doing is we are developing our intuition here that we'll need in order to be able to analyze the performance of algorithms. These are good questions. Any more? I think I had some. Any questions about that one, about estimating the time?
Can we do an example?
Yeah, the way, so there was a homework exercise that says if it takes 1 second to execute with how many? I forget.
1,000.
If it takes 1 second to execute with 1,000 data points, how many seconds does it take to execute if it's
10,000.
big 10,000, given these different big thetas? So the way you do that is you set up a ratio. So you say 1 second is to what? Let's suppose that your big theta is big theta of log n. So you would say if it takes 1 second to execute this many, log 1,000, did we say? If it takes 1 second, then the question is, how many seconds does it take to do what? 10,000. And then you just solve for t. So what you do, and here, let's just do it. So this t is equal to what? 1 second, and then it's the ratio of these two functions. So bring this up here. So this is LG 10,000 divided by LG 1,000. This is log base 2. LG is log base 2. And you just do those functions in there and just crank it out.
Just a constant.
Yeah, it doesn't depend on n.
Right, so like, I'm saying.
If it's big theta of 1.
Would you need to set it up in this way?
Well, you don't have to. It's all I want is a final answer. But you don't. But if it's big theta of 1, n doesn't even enter in. So therefore, well, let's do that one. So that part A.
Yeah.
So what's the answer?
It's just 1.
It's 1.
Oh,
One
yeah,
one
see,
second.
I was trying to put it in like
Well, I
that
mean,
equation, and then it was just a different, and I was like, that's not right. So okay.
well, it'd be what it'd be 1, and this would be 1 over 1.
Right. Yeah. See, before.
See, it would be 1 over 1. So 1 times 1 over 1 is 1. 1 second.
Okay.
Should we do the n? Is it possible that we're getting like an infinite number of years?
Yeah, that's kind of.
No, well, it's not infinite. Come on, there is no infinity. I mean, it's big.
Okay.
It's big, but it's not in. I mean, no. You should get all of these. You can get numbers.
Okay.
I think, right? What was What was it? Was it?
Got down to like 2 to the 9,000.
Yeah, 2,000.
Yeah.
Well, but didn't I say for that one to make it 10 to the some? What I think the problems. I think the exercise specified 10. Convert it to 10 to the something,
Over the years.
or I think.
It was just too much for the calculator, so I just.
Oh, you couldn't finesse that? Well, okay, I'll leave it up to you to see if you can finesse that. I mean, there should be some mathematical manipulations for you to get that. I mean, I've got a number for it.
Okay.
I challenge you. We are calculator bound here. So let's continue our skill at writing down recurrences. Remember, this is the first step. The first step is to write down the recurrence. The second step is to solve the recurrence. So we're still just doing the first step. So here, you guys have done binary search, right? Okay, so binary search. A is the array, low is the low, high is the high one, and V is the element that we're looking for. We're searching for V. So okay, and by the way, this is just pseudocode. I don't want to have to mess with all the syntax of C++. So how does the binary search work? If low, so remember, so here is low, here is high. So so normally we're searching between low and high, from low to high. So if low is greater than high, what happened? No, not an error. It's just it's not in there.
Yeah.
So we return -1 because and we'll say that -1 means that it was not found. Otherwise we return the element, the index. Okay, are you with me? So if it wasn't found, else what do we do? Mid gets what? Does it say there?
Low plus high divided by 2.
Yeah, low plus high. So that's the midpoint. Okay, the mid between low and high, the index. And then if V is, and by the way, binary search assumes that the array is what?
Ordered.
Sorted, it's in order. So if V is less than A sub mid, so here, if V, so here's mid, if V is less than A sub mid, that means it's between what? Between low and mid, so we look at it, search for it between low and mid minus 1. So we return binary search, but now this is a recursive call. Are you with me? Else what? If it's greater than, then it's a recursive call. So we're going to call one of those two, else we return mid and we found it. So what we're going to do is let's write down a recurrence for the worst case where we have to go all the way down, all the way down, all the way down. Okay, we find it at the very last one, or we don't find it at all. So can you write the recurrence for this? What do you think? So what's the shape? What is the shape of a recurrence? T of n equals base, and what do you think about the base case? I mean, let's do it just with big theta. Let's skip the 1, 2, 3. Yeah. Big theta of 1. And now what about the what about the recursive case? What about if low? Yeah. What about the other one?
Do you have to declare for what n?
Yes. Yes. So what is the n going to be when you return this binary search up here? What did we do with the binary search? What did we do? We cut it in what? Cut it in half. So n is going to be like high minus low. That's how many elements we're looking for. So you cut it in half. So what do you think? Silence is deafening. So it's big theta of 1 if n is less than or equal to 1. So if we're high is greater than low, so is everybody with me on this? N is the number of elements. It's like high minus low. So it's big theta of 1 if n is less than or equal to 1. But then what do we do? See here, because in that case, the statements that execute are if low is greater than high, then return negative 1. So that's this one, right? But otherwise, what will we do? We will either call what or what? Either do this binary search or this binary search, right? But either one of those, see, look, either one of those is T of n over 2. Because instead of searching for n elements, what do? We're cutting it in half and we're searching for what? N over 2 elements. So it's either this one or this one, but it's one. It's going to be one of those. So it's 1 T of n over 2. And then what about all the other stuff? There's no, all this other stuff is the big theta of 1. Now, does everybody see this? It's all the no, we're good. It's all the other stuff. Like in order to get to one of those, you have to do the if low is greater than high, then you have to calculate the mid, and then you have to calculate an if statement, and maybe you have to calculate another if statement. But that's just but yeah. So it could be like 1, 2, 3. It could be 4, maybe 5. But whatever it is, it's big theta of 1. Are you with me on that?
Yeah.
Yeah.
What about the last return that at the bottom?
Yeah, and then that's another one. Oh, we're doing worst case. Like if you could find it earlier, but we're assuming that you go all the way down to the end.
Okay.
See, this is a worst. I mean, in the best case, it would happen. You'd find it right away. First one, right in the middle. That's the one you're looking for.
Right.
Yeah. Okay. So now, you guys, does this look familiar? Figure 3.7. You programmed this, right? When you learned recursion. Towers of Hanoi, right? Okay, so how do you move n disks from peg 1 to peg, how do you move 4 disks from peg 1 to peg 3? You move what?
3 disks.
3 disks from peg 1 to peg 2, then you move what? 1 disk from peg 1 to peg 3, and then you move what?
3 disks.
3 disks from peg 2 to peg 3. So what happens is, in general, you move what? To move n disks from 1 to 3, you move n minus 1 from 1 to 2, n minus 1 from 1 to 3, and then n minus 1 from 2 to 3, right? And you guys have done this. Here's a little pseudocode solution to the Towers of Hanoi. Does this look familiar?
Yes.
Right? Good. I knew you would know this example. But look, if what is it says, so n is how many disks to move, f is the from peg, and t is the to peg, right? And so if n equals 1, then print move one disk from peg f to peg t, right? Otherwise, what does this I stand for? The intermediate one, yeah, I for the intermediate one. So the intermediate one is 6 minus f minus t. And so how does this work? Towers of Hanoi, what? You move n minus 1 from what? From the from to the intermediate. And then one disk from what? The from to the to, and then n minus 1 disk from the what?
Intermediate.
To 2. Okay, so now what's the recurrence? See, did you ever wonder how many, did you ever try to, what do you think your statement execution count is for Towers of Hanoi? Well, I mean, we should be able to figure it out after we get all these tools in place. The first thing to do is to write down the recurrence. What's the recurrence?
The first one is bit of 1. Big theta of
Yeah, big theta of 1, right. So the base case is going to be big theta of 1. But now what about the recursive one? What about the other one? Because
So would the first one be T of n minus 1?
yeah, okay, the Towers of Hanoi n minus 1 that's going to be t of n minus 1. Correct. That's a good observation. What about the middle one? Towers of Hanoi 1 ft. That 1 is just going to call what? That's just going to be a constant. So we can just count that as that's not a recursive call all the way down. So that can just be 1. We can count that as 1. But now what else?
Another.
Okay, so now can you tell me what is the recurrence? It sounds like we're good. We're really close. So what is the recurrence?
1 squared.
Not squared. Close, no cigar. You do it twice. Are you with me? So, okay, so it's theta of 1 if n equals 1, then it's 2t of n minus 1, and then plus big theta of 1. So here, the big theta of 1 is this, all right? And then the 2t n minus 1, it's t n minus 1, it's actually t of n minus 1 plus t of n minus 1. Are you with me? But t of n minus 1 plus t, a plus a is 2a. Are we good? Yeah.
Okay, so for that.
Yeah.
One, that's all.
Yes. So all that other stuff, that's all wrapped up into this big theta of 1. It's some constant that, yeah. Now, does everybody understand this? This is really a skill that we need to be able to develop. We need to be able to look at the code and write down the recurrence. Yeah.
I'm still struggling.
Do you see that we could replace that middle call with print move one disk from peg F to peg T?
Oh, because it'll just go to
To that one and then just come back.
Okay.
It's not going to completely go all the way, recurse all the way down.
Okay, sounds good.
Yeah, that was a good question, but you see that now, yeah. Okay, are we good? Is everybody good? Okay. Now that, and when we do these algorithms, we're going to do lots of recursive algorithms, and we're going to have to look and be able to write down the recurrence. And now we need to be able to solve the recurrences. Now, here's the thing. There are 4 standard, well-known techniques for solving recurrences. So at this point, we're going to assume that we have a recurrence, and we're going to solve it. So there's backward substitution, there's the recursion tree method, there's the guess and verify method, and there's the master method. And let me just tell you right off before we get started, you need to have seen all 4 of these. I'm only going to require you to do on an exam the guess and verify method. Okay? So we can but these are all standard techniques, and you should be familiar with them. Okay? So first, let's take a look at the backward substitution method. And here again, I'm not going to ask you to do a problem like this, but you should see how it's good to see how it works. So suppose we have this recurrence: t of n equals 1 if n is less than or equal to 0 equals t of n minus 1 plus 1 if n is greater than 0, right? So, and what we want to do is we want to solve for t of n. Now, do you see? This is t of n defined in terms of itself. So do you see what we mean by solving for t of n? We want to solve for t of n not in terms of itself. T of n is some function of n, not in terms of itself. Are you with me? So look, let's just start with T of n and just proceed systematically. What does this say that T of n is? It says it's T of what? N, no, n minus 1 plus 1. But wait, okay, well, that's T of n minus 1. But now, what does this recurrence say that T of n minus 1 is?
T of n minus 2 plus 1?
It's T of n minus 1 minus 1 plus 1, right? And then plus another 1. So does everybody see that it's this?
Yeah.
Is everybody with me? We just substituted into the recurrence. Is everybody clear on this? Okay. But now what is T of n minus 2?
T of n minus 3 plus 1 plus 1 plus 1.
Yeah, T of n minus 3 plus 1 plus 1. Now here comes the hard part. Dot, dot, dot. Now what's the last one? Well, how do we get to the base case?
T of 1 plus 1.
T of n what? The last one is, how do we get down to 0?
Of n minus 2.
Well, no, T
minus
of
n
n
minus
minus 3.
T of n minus n.
Oh, T of 0. Plus
Look, it's T of n minus 1, T of n minus 2, T of n, dot, 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 T of what? N minus n. Do you see what we're saying? All right? And so that means that we have piled up how many? N occurrences of 1. Are you with me? Because each time we go down by 1. Yeah.
Yeah, so you can replace the T of n minus n with 1. Right?
So n minus n, to answer your question, n minus n is T of 0. And up here, we know that T of 0 is 1, because T of n is 1 if n is less than 0. So this is 1 plus n. Does everybody see how that works? And then so T of n equals n plus 1. So now here we have T of n defined not in terms of itself. It's T of n. And so therefore it's big theta of what? Of n. Is everybody clear? Now this gets a little tricky. Because what if you have something like this? T of n equals 1 if n is less than or equal to 1. And it's T of n over 2 plus 1 if n is greater than 1. Now what happens is we start with T of n, which is what? T of n over 2 plus 1. But now what is T of n over 2?
T of n over 4.
T of n over 4 plus 1 plus 1. And then what?
T of n over 8.
T of n over 8 plus 1 plus 1 plus 1. And so now we're going to do the dot, dot, dot. But now what? How far down do we go till we get to T of n over n? It's going to be T of n over n, right? Plus 1 plus 1 plus dot, dot, dot. But now how many 1s are there?
No.
Or natural log base 2.
Actually, you're right. It's log base 2 of n. It's kind of tricky to it's kind of tricky to see. It's T of n plus it's T of 1 plus k, and the question is what is k? And that's 1 plus k. So what happens is you have to analyze. See, the first one is T of n over 2 to the 1. The next one is T of n over 2 to the 2. The next one is T of n over 2 to the 3. And the last one is T of n over 2 to the k. So what has to happen is n must equal 2 to the k. See, n must equal 2 to the k. And so if you take the log base 2 of both sides, this is log n equals k. So there are k occurrences of that, and so therefore T of n is 1 plus log n, and then so what's the big theta of this? What's the big theta? Big theta of log n.
Do you have to do like plus big theta of 1?
Oh, that's a good question. So big theta of 1 plus log n equals big theta of log n.
Why?
Aha, because
It just says so much.
yeah. Actually, we're gonna see these in a minute. Actually,
Is it? But what if it wasn't a log in there? What if it was
yeah. Then you have to.
something else?
Then we'll see. We are going to do some comparisons of different growths of different asymptotic bounds in a minute. But like I say, don't worry about this. I'm not going to ask you. But it's good for you to see it once. Right? Now, this next one, for sure, is complicated. This is called the recurrence tree method. And what happens is, let's suppose we have an example here where we have t of n is 1 if n equals 1, and 2t of n over 2. Now, this time it's 2t of n over 2 plus n. So can you see where this would come from? This would come from an algorithm that calls itself twice. There are 2 recursive calls. Each one is with an n over 2. And then also, for the other stuff, there's like a loop that executes n times. Do you see what I mean? That's the kind of an algorithm that could come from. Are you with me? So that n is how much work is done. So what you do is you set up, this is the call tree. You know what we mean by the call tree? In other words, t of n calls t of n over 2 once on the left, and then it calls it again on the right. And the amount of work that's done at that top level is, there's a loop that executes n times. And so here on the second level, t of n over 2 has a loop that executes n over 2 times, and then the one on the right, t of n over 2, also has a loop that executes n over 2 times. So there's 2 times n over 2, which is n, and so then you add up all the amount of work that's done, and you see that the total is nk. And so, but here the k, it's the same relationship. K is log base 2 of n, and so the conclusion is that t of n is big theta of n log n. But so now you've seen it. You can say you've seen it. And you might see it again sometime in your future computer science career. And it shouldn't be unfamiliar. But it's kind of very difficult to construct. It's a nice visual technique, but it's very difficult to construct in general. But this is the one you need to know. Guess and verify. Okay, so this is the one, and you'll have homework assignments, and I promise there will be this will be on the next exam. By the way, we have an exam coming up pretty quick, don't we? 28th, is that right? So, this is the guess, and the reason I like to emphasize this one is that this is a proof technique, all right? So you're given the solution, you prove that it's true, all right? So let's take a look, let's do a couple of these. So the first one is, let's suppose that we have an algorithm that has a recurrence of t of n equals 1 if n equals 1, and 2t n of n minus 1 plus 1 if n is greater than 1. All right? And what we want, and so do you see that one on the left, that is t of n defined in terms of what? In terms of itself. So that's what makes it a recurrence relation. We are claiming, and this is given, the solution is given, we are claiming that t of n equals 2 raised to the nth power, 2 to the n minus 1. We are claiming that that is the solution to that recurrence. Now notice that this over on the right, is t of n defined in terms of t of n?
No.
No, it's just 2 to the n minus 1. Does everybody see why that's the recurrence and this is the solution of the recurrence? Because it's t of n is some function that's defined not in terms of itself. Are we good? Now, how do you suppose we are going to prove this? What proof technique are we going to use if we have a base case and proof by mathematical induction? So how do you do proof by mathematical induction?
Base case.
Base case. Proof. Base case. Now, what is it that we're trying to prove? The one on the left or the one on the right? What are we trying to prove? No, the left is given. We're trying to prove the one on the right. Are we good? The left is given. That's the definition of t, which means we can use textual substitution in it. The one on the right is what we're trying to prove. So what do you suppose we should start with? Let's start with the whole thing. With these, we will start with the whole thing. With the base case, we'll start with the whole thing. All right? So what we're trying to prove is t of n equals 2 to the n minus 1. Now what's the very first?
T equals 1, or n equals 1?
Yeah, so what are you invoking when you do that? The base case. So we invoke the base case. So this equals, by virtue of the fact that the base case is n equals 1, and so now what do? Just plug in what? Plug in 1 for n. So what do we have? No, not T of n. T of 1 equals what?
Oh, yeah.
To the 1 minus 1, right? And now that we've got this, now what? We can do some math, right? 2 to the 1 is 2. 2 minus 1 is what? 1. So we do some math. That's T of 1 equals 1. So that's the math. But now what do we use?
Like inspect the,
Yeah, yes, now we can see that by the definition of, on the base case, by the definition of T of n, T of n says T of n equals 1 if n equals 1. So that's 1 equals 1, definition of T of n. So we invoke the definition of T of n, that's 1 equals 1. As everybody's clear on how to structure this. So always do your base cases like this. Start with the whole thing, just do these steps, and it'll be very mechanical. All right? But now comes the tricky part. Now comes the inductive case. Now, do you remember there is a big sentence that you have to write down for every induction proof that you've ever do in your whole life? Must prove something, assuming what? Something as the what? As the inductive hypothesis. As the inductive hypothesis. So here it is. Prove blank, assuming blank as the inductive hypothesis. Yeah, so what is the thing that we are trying to prove? T of n equals 2 to the n minus 1. So prove T of what? N plus 1 equals 2 to the what? N plus 1 minus 1. Are we good? Assuming what? T of n equals to the n minus 1 as the inductive hypothesis. You have to write this out. Your proof is incomplete without stating what it is that you're doing. All right, so that's the famous sentence. And now where do we now that we see, now what are we trying to prove? T of n plus 1 equals to the n plus. So now should we start with the left-hand side or the right-hand side? We're trying to prove T of n plus 1 equals 2 to the n plus 1 minus 1. So what should we start with? No, look, we're trying to prove this. We're trying to prove this whole thing. Should we do here and get to here? Should we start with the right-hand side and get it to this, or should we start here and get it to this? I think we should start with this and get it to this. Yeah? So here, T of n plus 1. Now, is everybody following every? Okay. So now, what does T of n plus 1 equal? Now, what should we invoke now? The definition. Definition of T of n. But now, because this is a definition, we can use textual substitution. It's T of n with what? N replaced by n plus 1. So if we do T of n with n replaced by n plus 1, what is it? 2 what? T parentheses n plus 1 minus 1 plus 1. 2 T n plus 1 minus 1. Right? Are we good? Does everybody see that? Textual substitution? Okay. But now what is n plus 1 minus 1? So by some math, that's 2 T of n plus 1. But now, sports fans, what do we have? We have the, no, there's no base case, no base case. No, don't, please don't say base. Please don't say base case. I'm sorry. I get, because we did the base case. We're not doing the base case anymore. It's the what? It's the inductive hypothesis. Students always mix up the base case with the inductive hypothesis. I don't know why. That's all right. You can repent. Okay. So now we invoke the inductive hypothesis, right? So by the inductive hypothesis, what is it? So what does the inductive hypothesis say? It says T of n equals what? 2 to the n minus 1. So this is 2 times what? 2 to the n minus 1 plus 1. These are all good questions. And now, what is 2? 2 is the same thing as 2 to the what? No. 2, just 2. 2 is the same thing as 2 to the what? 1. And then 2 to the 1 times 2 to the n is 2 to the... So if we do some more math, what do we get? and then minus 2, but then plus 1 is what? Minus 1, so boom. And look, that's what we were trying to prove. Are we good? Everybody good? Now, here's another one. Now, in that case, the recursion was minus 1. In this case, the recursion is going to be t of n over 2. All right? So now what we're going to do here is that this is a little tricky. Because in our induction case, we're going to, because each time we go through, we cut it in half. So in our induction case, it's going to be a little tricky. It's not going to be minus 1. It's going to be divided by 2 for the assumption. See, so this is it's a little different from what we just did. So let's suppose that we have t of n is 1 if n is less than or equal to 1, and t of n, and it's t of n divided by 2 plus 1 if n is greater than 1. What we want to do is prove that t of n equals log base 2 of n plus 1. Now what's the first step?
Base case.
Base case. And how do we always start the base case? How do we always do the base case? Start with the what? I mean, the whole thing. We always do the base case, start with the whole thing. So we start, t of n is log n plus 1. And what's the very first step always? Invoke the what? And by the way, how do we know what the base case is? It's up at the top. It says if n is less than or equal to 1. So we'll make it 1. The base case is n equals 1. All right? Is everybody clear? Okay. And so because the base case is n equals 1, what do we put? T of what?
T of 1.
Equals log plus 1. T of 1 equals log 1 plus 1. And what is the log of 1? 2 to what power?
0.
Yeah. So by some math, and 0 plus 1 is 1. And now what do we invoke? By the what? What's the reason now? Definition of t of 1. Yeah, definition of t of n. So it says it's 1, so 1 equals 1. Is everybody good? All right, here comes the famous sentence. Here it is. Inductive case. What's the sentence? Prove blank, assuming blank as the inductive hypothesis. T of
N plus 1.
no, see, because we're dividing. See, look, it's not plus 1 because you see, we're not subtracting 1 each time.
Yes, you were dividing.
So yeah, we're dividing by 2. So what did you say?
T of 2.
2n equals log what?
2n plus 1.
Plus 1. So t of 2n equals log 2n plus 1, assuming what?
All that stuff.
Well, assuming what? T of
T of n.
n equals log n plus 1 as the inductive hypothesis. Yeah, because the question is, why don't we say prove t of n plus 1 equals log 2n plus 1, assuming this as the inductive hypothesis. The reason we don't do that is because in the induction case, each time it calls itself recursively, it's dividing n by 2. It's not it's not doing n minus 1, it's doing n divided by 2. So we have to modify our inductive hypothesis.
And is it just for this case?
It's for all those cases where you have t of n over 2. Is everybody clear? This is a little tricky, but this is the way it's done. Okay. Okay, so now where do we start? We're trying to prove this over here, right? Prove 2n plus log 2n plus 1. We're trying to prove this. So should we start with the left side or right hand side? Actually, now you'll see why. We'll start with the left side. T of 2n. Now, what's our first step?
We substitute for 2.
Definition of t of n with n. This time it's with n replaced by 2n. So what is that? T of 2n over 2 plus 1, right? But what's 2n over 2? equals by some math t of n plus 1. And now what can we do? Do we invoke the base case? Yes or no? No. We invoke the what? We invoke the inductive hypothesis. And the inductive hypothesis tells us what? Log n plus 1. Now we're up a creek here, aren't we? Because what are we trying to get this to? The log of 2n plus 1. Here we have a log of n, and we have a plus 1, but then we have a plus 1. So we got the plus 1 on the end, but how are we going to combine the log n and then plus 1? What's another way to write 1? Equals by some math, log base 2 of 2. Are you with me? Because 2 to the 1 is 2. Is everybody good? But what's the log of a plus b? Well, sorry, what's the log of a plus the log of b? So the log of a plus the log of b is the log of a times b. So what do we have? Yeah, log of 2n plus 1, which is what we were trying to prove. Are we good? Okay, so those are the kinds of things that you do need to know how to do. You do need to know how to do to prove that a given proposed solution satisfies the recurrence relation by using proof by mathematical induction. Now this next one, the master method, is a cookbook method. And this is a very well-known result in the analysis of algorithms. And I'm only presenting here a basic version of the master theorem. There are more complicated versions of the master theorem that we're not going to get into, but if you're interested, you can research it. These are all well-known results, and you can look at all this stuff on the, you can Google all this stuff on the internet, and it's very well known. So here's the master method is based on the master theorem. And the master theorem says, let a be an integer, a greater than or equal to 1, b be a real number, b greater than 1, and c be a real number, c greater than 0. Given a recurrence of the form, now look at this. T of n equals 1 if n equals 1, and it equals a times t of n divided by b plus n raised to the c power if n is greater than 1. So that's just a general form. With, you know how you had the in algebra when you had the quadratic equation and you had ax squared plus bx plus c, and then you could just had to plug and chug with the numbers. That's what this is. You know, but it's for solving this recurrence. It says then for n an exact power of b, if log base b of a is less than c, t of n is big theta of what? If log base b of a is less than c, then t of n is big theta of what? N raised to the c power. It's just a cookbook. If log base b of a equals c, t of n equals big theta of n raised to the c power log n. And if log base b of a is greater than c, then t of n equals big theta of log base b of a. So it's just a cookbook. So what you do is you have a recurrence, like here's a recurrence. T of n is 1 if n equals 1. It's 2t of n over 2 plus n if n is greater than 1. Because all you have to do is identify what a, b, and c are. And then plug it in. Oh, so what's a? What is a? 2. Does everybody see that? B is what?
2.
B is 2. And what is c?
1.
C is 1. So does everybody understand? It's a is 2, b is 2, c equals 1. And then you just go back and you cookbook. But now what do we have to compute? We have to compute what? Log base b of a, and then compare that with c. So log base b of a in this case equals what? Log base what? 2 of what? 2, and log base 2 of 2 is what? 1, and what is c? C is 1, and c equals 1. So therefore, which case is it? Is it the first one, the second one, or the third one? This equals this. So it's the second case. Yeah? And so what is it? So it's big theta of what? Of n to the 1, so that's just n. Log of what? Log of n. And this could just, I mean, the difference between log of n and log base 2 of n is just a constant. So the big theta is the same. So therefore, this is just t of n is big theta of n log n. This is a little cookbook method. All right? Good deal. See you on Thursday.